Hey Radical Scientists, this is Mr. Giovanni creating a quick walkthrough video to help us with this week's electrostatic, should actually say gravitational force practice with our very first problem. Now, throughout this week, just to summarize really briefly, we went through a very rigorous process of data analysis with our gravity simulation, and now we have a tool to actually be able to predict a gravitational force in a lot of different circumstances. We have 5, not including that extra credit question, 5 different scenarios that I want you to practice with using this equation with our different sets of masses and distances. And we're gonna go and walk through the very first problem here together just to make sure we have a thorough understanding of how exactly to go from what we're given to whatever it is that we're looking for in these problems. So without further ado, hope this video explains a little bit more clearly how to solve these problems. They all look a little different depending on what you're looking for, so keep in mind the problem solving process is going to look different for these problems, but make sure you're following along with these steps to get a clear understanding as to how to use this equation. Without further ado, let's go. Alrighty y'all, so we're going to go ahead and get started here with our very first question, which asks 2 spherical objects have masses of 8,000 kilograms and 1,500 kilograms. These centers, their centers are separated by a distance of 1.5 meters. What is the gravitational force between them? Okay, as always, I want you to get used to asking 2 questions in order to get yourself started here. What are we looking for here? In this case, you see that if you were to reduce this question to one essential question, it is, what is the gravitational force? That is essentially what we're looking for. We're looking for our FG in this occasion. Okay, that is where we're headed towards. We're not done until we have that question settled. Second question, of course, okay, if we know what we're going for, where are we? What do we know? What do we have to work with? In this case, I always like to underline the numbers. I see here 8,000, I see here 1,500, and I see 1.5. Those are the numbers, but we need to make sure we know what these numbers are. Our kgs are our clue to indicate that this is some sort of mass. Okay, so what I'm going to write here is I'm going to write M1 is equal to 8,000, right? Apologize for the messy writing, y'all. I have writing this unfortunately with my finger here. M2, right? Mass 2 is actually equal to 1,500. Okay, and our distance, which again confusingly is represented by R, is this 1.5 meter. It says so there in the problem. Okay, I'm gonna ignore the units for now, only to be able to work on the numbers and emphasize the numbers here before we get going. The next part of this, now that we have our values here, looks like we have enough to start putting this into the equation. So when we write, right, that this gravitational force is equal to, I'm not gonna worry about that quite yet. M1, M2, and R squared in the bottom there. I'm gonna go and just substitute these numbers into the equation. Instead of M1, it says here M1 is equal to 8,000. I'm just gonna write 8,000 there. Okay, instead of M2, it says there it's equal to 1,500. I'm usually write 1,500 here, right? And of course, in the bottom, I'm gonna write 1.5. And then let's not forget that this value is squared. Okay. Here comes the calculation part. I'm gonna go ahead and just multiply the top numbers there. Pull out my handy dandy calculator here. Okay. And write 8,000 multiplied by 1,500 is equal to, it says there 12 million. It's a big number here. Okay, so I'm gonna write here again capital G. We apparently have 12 million here. I'm gonna write 12,000. That should be a comma there, 000. Okay, again, my apologies here. And this is all over 1.5 squared. Let me pull my calculator again and write here. What is 1.5 squared? Or if I can do that, 1.5 times 1.5. It gives me 2.25. Right? This bottom number here is actually 2.25 in the bottom there. Of course, we're still dealing with some type of fraction. I still want to reduce this even further, so I'm going to go ahead and now put all of this into my calculator. I want to simplify 12 million, this big number here, into the 2.25 in the bottom, which gives us Well, there's a lot of 3's. We're going to reduce it to 5, 3, 2, 3, 3, 2, 3, just after the decimal point there. Okay, let's go back here. We're going to go ahead and keep writing here. G, 5, comma, 3, 3, 3, comma, 3, 3, 3. And unfortunately at this point, we can't ignore that G there that's bugging us. This, of course, once again, as a reminder, is our gravitational constant, right? If you take a look into our little figures here to help us sort out what all of these letters mean, that is that number, and we're just looking at the units. I'm gonna go ahead and actually write it down here. We can, instead of G, right, I'm gonna follow over here, that number 6.674 times 10 to the negative 11. That is our gravitational constant for anything that involves gravity. And we're going to go ahead and write that number that we said we're still working with, 5333, 333. Now, my recommendation for these problems is always to focus on the numbers and the 10 to the exponents separately. So we're just going to focus on, like I mentioned, the numbers first, the 6.674 and the 53333. We're going to go ahead and put those in the calculator to see what number we're getting. I still have this here in my calculator, thankfully, so I'm just going to multiply this by 6.674, which gives me some type of 35 million figure. Let me write, for my sake, 35,594,666. Okay? Again, that's, I believe, 35,594, and I believe it's just 6 after that. Yeah, I can round it to 7 just to be safe there. And now we're dealing with the 10 there, right? We still have to not forget that this is all being multiplied times 10 to the 11. Now, this is a big number, and if we want to go ahead and use the convenience of scientific notation, what we're going to have to do is, let me actually move this all up here. Now we know our question, we have to just simplify. What we have to do is actually go ahead and aim to have this answer in the following format, into some type of 3. For our sake, we're going to simplify to 3 significant figures, 0.5, that 9 makes that next 5 a 6, 3.56, right, times something. Now, of course, these are not the same numbers, right? We have 35 million and then 3.56. Again, scientific notation has us only look into the number after that decimal there. So what we need to do is we need to count for that jump there with the decimals. So let's count with me how many figures they had to jump through to go from the decimal right here into the one right after the 3. So we go from 1, 2, 3, 4, 5, 6, 7 places that the decimal has to move. In other words, what right here is times 10 to the 7 to account for the fact that in order for these numbers to be the same, right, the 35 million and the 3.56, the 3.56 needs to be multiplied by a 10 to the 7th there. And of course, keep reminding ourselves, we still need to include the fact that this has a 10 to the negative 11 there. This looks a lot more simple. The number is pretty much then done at this point, right? We know for sure it's going to be 3.56. And now the only thing we need to worry about is, of course, I'm so sorry, that looks more like a G. Let me undo that and make this 6 here. What we need to do now is simply work on that 7 and that 11. Remember, when we have these exponents there, a convenient, quick rule of thumb is simply to have those numbers, when they're multiplied, added together, right? So what would 7 and 11 be added together? Well, I think I already know, but let me just check with my calculator here. 7 plus negative 11 is equal to, well, that's actually 7 plus 11. Let me do 7 plus 11 negative is equal to negative 4. When we write this number as 1, we are left with just 3.56 times 10 to the negative 4. This would be our solution for problem number 1.